Welcome to week 2 of linear algebra. Today we're looking at chapter 1, section 2, bases for a vector space. Last week we defined what is a vector space over a scalar field K. Now we're looking at what is a basis for a vector space. Before we define a basis, though, we first need to define what we mean by a set of vectors being either linearly dependent or linearly independent. So here we go, section 1.2. Let Vk be a vector space over the scalar field K. Let V1 through V sub n be a set of n vectors in V. We say that set of vectors are linearly dependent over K if there exist scalars a1 through an that are not all 0, so that the linear combination of the VI-AIs or AI-VIs is equal to the 0 vector. If all scalars have to be 0, then they are linearly independent. All right? So once again, when you have a set of vectors, V1 through Vn, they're linearly dependent if there exists a set of scalars that are not all 0, where the linear combination equals the 0 vector, and they're independent when all of the scalars have to be 0. Example 1, let V be Kn, let E1 be the vector 1 and all zeros afterward, E2 would be 0, 1, 0, 0, 0, dot, 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 E sub n be 0, 0, 0, 0, 0, and then 1 in the last position. These are called unit vectors in Kn, and they are linearly independent. We see that by taking a linear combination of scalars, a1, e1 plus a2, e2 through a sub n, e sub n equal to 0 vector. But when you do the computation, you'll notice that you simply get the ordered n tuple, a1, a2 through a sub n. That's equal to the 0 vector, so that immediately means that all of the scalars ai must be 0. And so the unit vectors in Kn are linearly independent. Okay, example 2. Let V be the vector space of all functions that we talked about in section 1 in a variable t, where t is an element of S, so that the image f of t is in the field K. Let's look at a set of functions f1, f2 through f sub n in V. We say that the set of functions are linearly dependent if there exist scalars a1 through an that are not all 0, so that the linear combination is equal to 0 for all t in S, that is, for all elements in the domain set S. Okay? And similarly, the functions would be linearly independent if all the scalars have to be 0. All right? Now here's another example. Let's consider the two functions e to the t and e to the 2t, and let us show that they are linearly independent. So to show that these two functions are linearly independent, take two scalars a and b, look at the linear combination, set it equal to 0 for all t and r. Now here's a trick that often works well for function spaces when you're looking at linear combinations. Take the derivative on both sides. Differentiate that relation. So if you take its derivative, you get ae to the t plus 2be to the 2t equals 0. Now you have a system of two equations and two unknowns, a and b, and then you can solve for a and b. Subtracting the first equation from the second yields be to the 2t equal 0. But remember that e to the u, or e to the t or 2t, is non-negative for all t. So that means that b has to be 0, and then hence a must also be 0. So we find that those two vectors are linearly independent. You might remember that vectors like functions e to the u or e to the t, those often arise in differential equations. All right. Now, what is a basis for a vector space? A basis for a vector space, here's the definition. Let Vk be a vector space. Let V1 to Vn be a set of n vectors in V. We say that this set of n vectors form a basis for V if two things are true. Number one, they are linearly independent. And then number two, they span or generate the vector space. That is, for every vector V in V, it can be written as a linear combination of the basis vectors. The first and very important example is that the unit vectors, E1, E2 through E sub n, that are known as the standard unit vectors, form what we call the standard basis for Kn. Standard basis. So the E sub i's, E1, En, are always a basis for Kn. And it's the normal, usual basis that we're used to working with in Kn. As another example involving functions, let W be the span of the two functions, e to the t and e to the 2t. All right. Then those two functions form a basis for W. We already know that they're linearly independent, and we're by definition saying that they span W, and so hence they are a basis. Now, Theorem 2.1 gives us a way of showing the uniqueness of linear combinations for linearly independent vectors. It is a uniqueness theorem, so let's look at it. Theorem 2.1, let Vk be a vector space and let V1 through Vn be linearly independent vectors in V. All right, let's take two sets of scalars, x1 through xn and y1 through yn. All right, now if you take the linear combination of the vi's with the xi's and set it equal to the linear combination of the vi's with the y sub i's, it must be the case that x sub I is equal to y sub I for each I, going from 1 to n. This is a uniqueness theorem. And the proof is simple. If you subtract the right-hand side over to the left-hand side and set it equal to the 0 vector, rearrange and collect like terms, you see that what you get is x1 minus y1 times v1 plus ... plus xn minus yn times v sub n equals 0 vector. But remember, v1 to vn are linearly independent, hence the scalars have to be 0. That means that x sub I minus y sub I has to be 0 for each I, hence x sub I equals y sub I. This allows us to define the coordinate vector of a given vector, okay? Now, let Vk be a vector space over scalar field K, and let V1, V2, ... through V sub n be a basis for V. And normally I should have written that the letter B equals that set of vectors. Let V be any arbitrary vector in the vector space V, and represented by the linear combination x1 v1 plus x2 v2 plus dot 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 plus x sub n v sub n. Then the coordinate vector of V relative to that given basis B is, and here's my notation for it, square brackets V sub B equals the ordered n-tuple of the scalars x1, x2 through x sub n. So this is, you have to have that uniqueness theorem before you can have the coordinate vector. So anytime you have a basis for a vector space consisting of n vectors and an arbitrary vector v and v, we now know that any vector v and v can be written as a unique linear combination of scalars x1, x2 through x sub n. And those unique scalars form what we call the coordinate vector of that particular vector v relative to the given basis b. All right, so there's the definition of a coordinate vector. All right, let's look at some examples. All right, example 3. Let V be the subset of function space spanned or generated by those two vectors that we just talked about earlier, e to the t and e to the 2t. Okay? Let f be a function in this function space with f of t equal 3e to the t plus 5e to the 2t. Then the coordinate vector of f relative to those two functions is simply the ordered pair 3, 5. Very simple, isn't it? Okay. Now, look at example 4. Show the following two vectors, 1, 1, and -3, 2, are linearly independent, obviously in R2. Okay? So to show they're linearly independent, we take two scalars, a and b, real numbers, with the linear combination of our two given vectors, and set that equal to the 0 vector, which of course for R2 is the ordered pair 0, 0. And that gives rise to a system of two linear equations in the two variables a and b, which are very easy to solve. You can solve it by subtraction and substitution, and you quickly get that a and b have to both be 0. Or using methods of Math 2260 and matrices that we're going to be using, you take the matrix whose columns are the coefficients of the linear system. So you get the first column is the 1, 1, the coefficients of the two a's, and the second column is the coefficients of the b's, -3, 2, and the third column are the zeros on the right-hand side. You might recall that's called an augmented matrix. And you solve the augmented matrix by doing reduction, row reduction. You reduce it to reduced row echelon form on the calculator, and you get 100010. Now that tells us immediately that A has to be 0 and B has to be 0. So those two vectors are linearly independent vectors in the xy coordinate plane, or R2. All right, example 5 is another example in R2. Here, we want to actually show that the two vectors we worked with in example 4 form, in example 6, we're going to show they form a basis, but we're going to do an example in example 5 by finding the coordinate vector of a given vector. So example 5, find the coordinates of the vector 1, 0 relative or with respect to the two given vectors, 1, 1, negative 1, and 2. So that means we have to find scalars a and b so that the linear combination of those two vectors equals our given vector 1, 0. You multiply the scalar inside the vectors and add corresponding coordinates, and it gives you a system of two equations and the two variables. So you get a minus b is 1 and a plus 2b equals 0. And you can solve it by subtracting one from the other and substituting one into the other. And you get a is equal to 2/3 and b is negative 1/3. Or using matrices with row reduction, with the augmented matrix of coefficients, row reduce the augmented matrix of coefficients, and you get the E1, E2 vectors on the left side, and on the right side you see that you're getting 2/3, negative 1/3. And so that means that the coordinate vector of the vector 1, 0 is the vector 2/3, negative 1/3. I might could show you briefly how you do that on the calculator. Here's my calculator. You go under second function x inverse, and let's edit our first matrix, and it's going to be 2 rows and 3 columns. However, when working on the calculator, it's probably best for it to be square. So I'm going to add a row of zeros to the bottom of this system to prevent me from getting a calculator error. So make it 3 by 3 on the calculator. And we're going to input, we've got 1, negative 1, 1. 1, 2, 0. And then 0, 0, 0. That's to guarantee that I don't get a error when I do the row reduction. Second function, x inverse, right arrow key to the math menu, upper arrow key to option B, RREF, row reduced echelon form, second function, x inverse, choose the first matrix A, close the parenthesis, and you are getting 2/3, negative 1/3. You see a decimal. If you do math number 1 fraction, then you have it 2/3, negative 1/3. So that's how you do it on the calculator, and you see then that the coordinate vector is 2/3, negative 1/3. Okay. Now next, example 6, we want to actually show that those same two vectors, 1, 1, negative 1, 2, form a basis for R2. Should have done this one before example 5 actually. But nonetheless, what do we need to do? We have to show two things. We have to show, number 1, that they are linearly independent, and number 2, they span or generate R2. Okay? First, we're going to show that they are linearly independent. Linearly independent. Okay? So to do that, we take our two scalars, a and b, with the linear combination of those two vectors, set it equal to the 0 vector, 0, 0, and you get a system of two equations and the two variables a and b, and you get a is 0 and b is 0, or do it by matrices with coefficients, row reduce it, and you also see that a and b have to be 0. So the two vectors are linearly independent. Now, the second part, you can't just do in a calculator. You have to do by hand. You want to show that these two given vectors span or that they generate the vector space. Okay? So that means that if you take an arbitrary ordered pair, A comma B in the xy plane or R2, there have to exist scalars x and y so that arbitrary vector AB can be written as a linear combination of the given two vectors, 1, 1 and negative 1, 2. So take two scalars x and y, x11 plus y times negative 1, 2 equal to A comma B. And again, multiply the scalars inside the two vectors, add the corresponding coordinates, and set the corresponding coordinates equal to A and B, respectively. So again, there's a system of two equations and two variables. And solve those two equations, subtract the first one from the second one. You get 3y equals b minus a. So you see then that y is b minus a over 3. Then substitute that in the first equation, and you get x equals y plus a, and then substitute what y is, namely b minus a over 3 plus a. So that tells us that for any ordered pair in R2, there do exist scalars x and y that are determined by the two coordinates a and b. So you can calculate what the coordinate vector is given any ordered pair and given this particular basis as your example. Okay? All right, next is a very important concept called a maximal subset of linearly independent vectors. Now, if we have a set of n vectors, v1, v2, dot, 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 through v sub n, in our vector space V, let R be a non-negative integer less or equal to n. All right. And then take a subset of that set of n vectors, v1, v2 through v sub r. All right. We say that that subset is a maximal subset of linearly independent vectors if two things are true. First, they have to be linearly independent. And then second, if we add another vector to them, v sub I, where I is greater than R, then that set, V1 through VR, in addition to VI, becomes linearly dependent. That's why it's called a maximal independent subset. Okay? Now, the proof is a little involved, but I do want to go through it with you. All right? So here we are. Now, that's the statement of theorem 2.2. Okay? Here it is, theorem 2.2. Now, so here's what we have. Okay? We have our n vectors, v1 through vn, that span the vector space, okay? And what we're doing here is called reducing a spanning set to a basis, actually. So what we're wanting to see is that we can take that set of n vectors and throw away the linearly dependent vectors out of that set. Okay? All right, so we have a subset of R vectors. Okay? They are independent. So now we only have to show that they span or generate the vector space. Theorem 2.2. All right, so we got a spanning set, and we have a maximal subset of independent vectors within the spanning set. So they're given to be independent. Now we want to show they span V. Okay? That's our goal. Our goal is to show that for any vector V in V, that there exists scalars C1 through C sub R with V equal the linear combination of C1 V1 through C sub R V sub R. Okay? Now we know by hypothesis that there exists scalars C1 through C sub N with any vector equal linear combination C1 V1 all the way through C sub N V sub N. Okay? So our first step then will be to show that for each of these VI's where I is greater than R and actually less or equal to N, that it can be written as a linear combination of its predecessors, V1, V2 through V sub R, okay? By hypothesis, and that is that we have a maximal set of independent vectors, and also now given V sub I, there exists scalars x1, x2 through x sub R and another scalar y added to those, not all 0, so that the linear combination of the VI's x1 V1 through xr VR plus y V sub I equal a 0 vector. Now, not all 0. Now, since the VI's from 1 to R are linearly independent, that means that the scalar y cannot be 0. If the scalar y were 0, then that would contradict our hypothesis that V1 through VR are linearly independent. See, if y were 0, then one of the other x sub i's would have to not be 0, making our V1 to VR linearly dependent. But we know by hypothesis that they are linearly independent, so it gives rise to a contradiction. Okay? So since y is not 0, we can solve our vector equation for V sub I because we have to divide by y, and we can't divide by y unless y is not equal to 0. Can't divide by 0. So if you solve the vector equation for for V sub I, here's what you get. V sub I equals negative x1 divided by y V1 minus x2 over y V2 minus minus x sub R over y times V sub R, okay? But remember, V is a linear combination of all of the VI's from V1 to Vn, right? We know that already, okay? Now, if you take that combination and then where I is greater than R, in that relation, we can replace each VI where I is greater than R by a linear combination of V1 through V sub R. And then once we've done that, we can rearrange and collect the like terms so that we now have the vector V expressed as a linear combination of V1 through V sub R. Hence, they're linearly independent. Now we've also proven that they span the vector space. Therefore, V1 through V sub R form a basis for the vector space. Now, this theorem, as I said earlier, 2.2, is referred to as the means by which we can reduce a spanning set to a basis. Okay? And I'm going to close this video with the following example. It's not in the book, but I want you to refer to a handout in Brightspace in your D2L under your content browser. Go under handouts and look at the first handout, Basis and Dimension from 2260 Vinay Bishop book on page 3. Page 3 of that handout, Basis and Dimension 2260 book. And it says Theorem 1, and then below that, the procedure for reducing a spanning set to a basis. What you do, let's look at my example that I have handwritten on the right-hand side. Let V be R2, and let our set of spanning vectors be 1, 1, negative 1, 2, and 4, negative 8. Let those three vectors be a spanning set for R2. Find, now I said the, it's actually not just a, but the, there's actually only one, maximal linearly independent subset of that set. All right, using matrices with row reduction, here's how we do this. Take those three vectors that were given, form the matrix whose columns are those vectors. Columns, not rows. The vector, the first column is the vector 1, 1. The second column is the vector negative 1, 2. Third column is the vector 4, negative 8, okay? Row reduce it to reduced row echelon form. And again, on the calculator, you probably have to add in a row of all zeros and make it 3 by 3 so you don't get an error in the calculator. And you get columns 1, 0, 0, 1 and 0, negative 4. Now, what this means is the following. In the row reduced echelon form, notice the columns in the reduced form. The first column is E1. The second column is E2. Now, the unit vectors E1 through E sub n are called elementary vectors. An elementary vector is a vector that has only one 1 and all the other entries are 0. But that third column there, 0, negative 4, is non-elementary, not elementary. Now that means that that third column is linearly dependent on the previous two independent columns. But what that means is the following. That means that the third vector, V3, can be written as a linear combination of the first two vectors, V1 and V2 here. And the scalars that form that dependency are the entries of that column, namely 0 and negative 4. So that means that V3 is equal to 0 V1 minus 4 V2, or simply V3 equals negative 4 V2. Hence, from those three vectors, V1, V2, and V3, the first two, V1 and V2, is the maximal linearly independent subset. In other words, that reduces the set of three vectors that we gave to start with down to being a basis for, in this example, R2. And if you look on the left-hand side, you'll see an example of vectors that are in R4. And you're given 5 vectors in R4 and you want to reduce them to be a basis for a subspace in R4. So you do the same thing. You take the vectors that were given in R4, write them as the columns, not rows, columns of your matrix, row reduce it to reduced row echelon form, and then you notice that vectors v1, v3, and v5 correspond to elementary vectors, where v2 and v4 are non-elementary. So that means you want to throw away vectors v2 and v4 so that the three that are remaining, namely v1, v3, and v5, form a maximal linearly independent subset, and they form a basis for a subspace of R4 with those three vectors. Okay, that concludes our video for this section. Our homework is on pages 14 and 15. I want us to work on all exercises 1 through 10, but you'll only be turning in number 4 and number 9. It is listed as homework 2 in the assignment folder in D2L. That concludes our video for section 1.2.